Alright, thanks for watching and welcome to the antiderivative derivative club. And the first rule of the antiderivative derivative club is you do not talk about the antiderivative derivative club. Just kidding, here's a whole video on this. And this is really neat. It has to do with calculus a lot, in fact. Because one of the first things you learn about integrals and antiderivatives is that if you take an antiderivative, so the indefinite integral, and you differentiate that, you get your function back. So in other words, the derivative of the antiderivative is the function itself. For example, if you differentiate x squared, then you get x cubed over 3 plus a constant. And if you differentiate that, you indeed get x squared back. But what if you do the opposite? What if you do the integral of the derivative? Do you get your function back? Well, let's see. If you take the integral of the derivative of x squared, you get the integral of 2x, and you get x squared over 2 plus a constant, which is not the same. Sorry, you get x squared plus a constant, which is not the same as x squared. So, even though the derivative of the integral is the function, the integral of the derivative is not the function. It's really the function plus a constant. So strictly speaking, integration and differentiation are not inverses. If we had inverses, we would have both those properties. And you should compare this to the formula for inverses. F of f inverse of x is x, and f inverse of f of x should be x. So in this case, I guess a differentiation is sort of a left inverse to integration, because we have this property, but we don't have this property. But what I want to show in this video is, in some sense, these still are inverses. And in fact, there's some way of defining or viewing integration in a sense that we do have those two properties that hold. And this is the goal of this video, and also just to show you how pedantic mathematicians are about defining things. So, how would you define integration so that we do have that both of them are pure inverses? It has to do with the concept of equivalence classes. So here's the first step. Let's define some new operation like an equality, but what's called an equivalence relation. Say that f and g are similar. So f is similar to g if f minus g equals to a constant. And the reason I write squiggle is because it's indeed an equivalence relation, and you can indeed check that the three properties of equivalence relations are true. Namely, f is equivalent to itself because f minus f is 0, which I hope we can agree that 0 is a constant. If f is equivalent to g, then g is equivalent to f. Yes? Because if f minus g is a constant, let's call it c, then g minus f is minus c, which is still a constant. And lastly, if f is equivalent to g and g is equivalent to h, then f is equivalent to h. Indeed, this is also true. If f minus g is a constant and g minus h is another constant, then f minus h is just the sum of those two constants, which is still a constant. So indeed, squiggle is an equivalence relation, and what that means is it's just like an equality. So it's like a weird version of an equality. And here's the important thing about equivalence relations. What it does it takes all of the family or universe of all the functions and splits it up into classes. Namely, it's the equivalent of splitting up the world in a country. Because what is, for example, the definition of the United States? Is everyone who's sort of related to where I am, you know. I live in the US, and then anyone else who lives in the US, they're also in the US. So it's like the whole country is like that. So in particular, the country of 0 is any function that's equivalent to 0. So any function whose difference with 0 is a constant, so they're like 0 is in it, the function 1 is also in it, because the 1 minus 0 is a constant, the function 2 is in it, because 2 minus 0 is a constant, and in fact, this is the country of all the constant functions. On the other hand, you have the country of x. Any function such that f minus x is a constant. So x is in it, x plus 1 is in it, x minus square root of 2 is in it. So essentially x plus any constant. Or e to the x, the kingdom of e to the x. It has e to the x in it, e to the x minus 3, e to the x plus pi, etc., etc. So you can already see that the country of a function is just any function of that function plus a constant. Alright, good. So again, equivalence relations are good because they partition the functions into nice classes. And now we want to define our new integration operator. So that was step 1. We just partition functions into equivalence classes. Now define a new transformation. Step 2. And just one little thing. So again, as I said, we took the space of all functions and we partitioned them. So 0, x, e to the x, etc., etc. The set of all those classes, we call it squiggly f. So f is just a set of all equivalence classes. For example, you know, the equivalence class of 0 is an f. Or the equivalence class of e to the x is an f. So if you want the set of all countries, and careful, that's not quite the same as just the whole world, because technically the whole world is a set of all people. And so a person is not a country, unless you're your own country. So strictly speaking, like functions e to the x or 0, they're not elements of squiggly f. It's really the classes that are elements of squiggly f. Like for example, in the United Nations, like, you know, Austria is part of the United Nations, but it's not that like Arnold Schwarzenegger is part of the United Nations. It's really the set of countries. Okay. Of course, you can think of, yeah, well, there's representatives and stuff, but no, that's too much. We're doing math here, okay? So f is a set of all equivalence classes, and define the new integral, and I still write it as integral because you see why, from the set of functions to those classes. So for any function, you assign me a country. So, and in fact, that's exactly what we're doing. Basically for me, you're assigning just the country where I live in. Except we have to do some modification. So define integral to the set of functions to you know, those classes. And so what is the input of integral? The input of integral is just a function. And what it spits out is the class of an antiderivative of little f. So f is an antiderivative. of little f. For example, the integral, so the new integral of x squared becomes the class of the function 1/3 x cubed. So in other words, it takes a person or a function as input and gives you the class of the antiderivative. So it takes, in this case, the citizen x squared as an input and assigns it the country of 1/3 x cubed. It says, hey, you have to go to this country. It's not very nice, but that's how it is. Okay? And moreover, so one little thing though we have, it is in fact well defined because because the question is, well, does it matter which antiderivative we pick? And I'm claiming that no matter which antiderivative you pick, you're still in the same country. Because it would have been a problem if, for example, the class of 1/3 x cubed is not the same as the class of 1/3 x cubed plus 1. Because then you would be in two different countries even though you're the same citizen. So, note, well defined, so it's indeed a legit function. Because suppose you have two different antiderivatives of f. If f and g are two antiderivatives of little f, well, there is this theorem that just says if you have two antiderivatives, then they just differ by a constant. Then f equals to g plus a constant. And again, that follows because if you differentiate it, the derivative is 0, so you get that it's a constant. And so in particular, f minus g is a constant, so f is equivalent to g. So f and g, in other words, are indeed in the same country, and in particular, the equivalence class of f is the same as the equivalence class of g. Which means really we can just pick any antiderivative of f and we still get that the integral of f equals to the integral of f. Would have been a problem if those two are not the same. So, indeed, it makes sense. This new integral makes sense, okay? And essentially, the joke is we're just saying that the integral of f is capital F plus a constant. But we're just being super pedantic today. Okay, we define a super integral operation. Now we want to define a super derivative operation. Also, define prime from the countries to the functions. So you see, integral went from functions to those countries. Prime goes from countries to those functions. And we just define it as follows. Namely, if you take the derivative of a country, it just gives you f prime. Now, of course, you might be like, this makes no sense. What if we have two different functions? Well, turns out it's not a problem. It's still well defined. Because suppose f and g are two different functions, but in the same country. So if the country of f equals to the country of g, then by definition, it means they have to be related. Then f is equivalent to g, so by definition, f minus g is a constant. So even though f and g are not the same, it's just f is a constant plus g. So then f equals to g plus a constant, but then the derivative of f is g plus a constant prime, and that's g prime. So indeed, if the two classes are the same, even though f and g are not the same, the derivatives are still the same. So again, it doesn't matter which citizen you start picking, because if you differentiate this country, it will always give you the same answer. So it is a well-defined thing. So in other words, the derivative of f, the class of f prime, equals to the derivative of the class of g prime. Okay, very good. So now we define two operations, the superintegral and the superderivative. And now, why did I define that? Because I want to show you now that the superderivative and the superintegral are in fact inverses to each other. So now here comes the most important part, the claim that both of them are inverses. Step 3. Claim, namely, the integral, and again, I want to remind you what those operations are. So, we have, this is the set of functions. We have the superintegral. What does it do? It takes a function as its input and spits out the country of one antiderivative of f. And on the other hand, we have the superderivative, which takes a country as an input and spits out just f prime. And we saw this is not a problem. This is indeed well defined. And so now I want to show you that, first of all, if you take the superintegral of the superderivative, you get our original function back, except careful about the domain. So the domain of the superderivatives are countries. So we want to show that this is true. In other words, if you take the superintegral of the superderivative of a country, you get the same country back. And indeed, let's just use the definitions. So, the superintegral of the superderivative of f, you just use this definition, and we get that this is equal to, again, just by definition of that, that's equal to the integral of f prime. Okay. And now, what is the superintegral of the ordinary derivative? Notice f is an antiderivative of f prime. Because if you differentiate little f, you get f prime. So by definition of the superintegral, you just take the country of one antiderivative of your function. In particular, little f is one antiderivative of f prime, so it's really the class of f. And indeed, therefore we have that the superintegral of the superderivative is the country of f. Now let's show the other way. Let's show that the superintegral of a function, and so let's show that the superderivative of the superintegral of f, let's show that the superderivative of the superintegral of f is just f. Well, let's see. What do I want to say? No. Let's now show that the superderivative of the superintegral of f is just f, and very important, so the superintegral of f gives you a country, and you differentiate that. Well, what is the definition of the superintegral? You just take an antiderivative of f, and you take the country. So by definition of the super integral, this is what it is. And then all you do, by definition of the super derivative, you just take the derivative of capital F. And again, this is well defined. And remember what was capital F? It was an antiderivative of little f. So by definition, capital F prime is little f. So indeed, in this sense as well, we get that the super derivative of the super integral is in fact your function. So if you define those super operations, then you indeed get that the integral and the derivatives, they're inverses of each other. And what am I really saying? I'm saying just a simple fact that if you ignore your constants, then in fact derivatives or integrals are inverses. But we had to make this rigorous by defining those countries, which is nice. It's a math geography lesson. Alright, so if you like that and you want to see more cool math, please make sure to subscribe to my channel. Thank you very much.